Hello students, welcome to the another video. Today we will discuss one theorem on limit points. So the statement of the theorem is let xd be a metric space. Let xd be a metric space and A is subset of x is subset of metric space xd. Then the set A is closed. A is closed if and only if A contains, the set A contains all its limit points, xd be a metric space, A is subset of metric space xd. Then A is closed if and only if it contains all its limit points. This is the relation between closed set and the limit points. As we discussed in the previous video, the set of limit point is x is said to be limit point of this set, suppose A, whenever for all radius, for all r greater than 0, if we draw the open sphere with that radius centered at x, then that open sphere must intersect, that is intersection of that open sphere with A must be non-empty, that is that open sphere, if we intersect that open sphere with A, then their intersection must contains at least one point other than the center. Now this theorem is xd is metric space and A is subset of x, then the set A is said to be closed, this subset of metric space x is said to be closed if and only if it contains all its limit point. If any set A contains all its limit point, then we say that that set is closed and A is closed, then that set A contains all its limit points. So in the notes that I have given you in the description of previous video, there is one correction in that notes. The notation of complement of A is A complement, not that this notation is set of limit points and this is the notation of complement of set. So A complement is the notation, there is mistake in that notes, so just make that correction. Now we will see the proof of this theorem. So here we have given that xd is metric space, also we have given that A is subset of that metric space xd, and we have to, first of all we have to suppose A is closed and our claim is A contains all its limit point, that is you can write A contains all its limit point means this all set of all limit points is contained in A. A contains means set of limit points is subset of A, properly contained. A contains all its limit points means all the limit points are in this set A. So first of all we will suppose A is closed. We have given that xd be a metric space, and A is subset of x. Now first of all we will suppose A is closed. A is closed set. A is closed set means A contains its interior as well as its boundary. A set is said to be closed if its complement is open. So A is closed means A complement is open, that is x minus A is open set. Now our claim is A contains all its limit points, that is set of limit points is totally contained in A. A contains all its limit points. So this is our claim. So to prove this set of limit points of A is totally lie inside A, we have to take just one element of this set A, limit points of A, and we have to prove that x again belongs to this set A. To prove any set is subset of another set, we just take one element of this set and prove that element is also in this set. Because of that arbitrary element, we say that all the elements of this set are totally in this set. Now let x belongs to limit point of A, that is x belongs to set of limit points means x is limit point of A. This implies that is x is limit point of A. X is limit point of A. Now, x is limit point of A means for any radius, if you draw the open sphere, then that open sphere intersection with A is contains at least one point other than this x. So, using the definition of limit point, we can write hence any open sphere centered at x, that is open sphere with any radius, any open sphere centered at x contains at least one point of A, contains at least one point or one element of A other than center. Other than center means center is x, other than x. Hence, any open sphere centered at x contains at least one point of A other than x. This is by definition of limit point. The definition of limit point was XD is metric space. Suppose this set A, then the limit points of A are just those elements of x. If you take that element as center, and for any radius, for smallest one or the largest one, for any radius, if you draw the open sphere, then that open sphere intersection with that A is non-empty. That is, the open sphere must contain some elements of A other than this center. So, using definition, we can write here x is limit point of A. So, any sphere centered at x must contain at least one point of A other than that center. Now, our claim is we have to show this element of A in limit point of A is again element of A. So, to show that, we have to show this x belongs to A. To show that x belongs to A. Show that x belongs to A. Now, this we will prove by using contradiction. Contrary, we are going to suppose this x does not belongs to A, that is x belongs to A complement, x belongs to A complement. Now, x belongs to A complement means x belongs to x, but x does not belongs to A. So, x belongs to A complement implies that this x belongs to x belongs to whole metric space x, but x does not belongs to A. This is the set of complement. Now, this x belongs to A complement, and our supposition is A is closed set, but A is closed set. A is closed set means A complement is open. This implies A complement is open set. A is closed. We say that set A is closed whenever its complement is open. Now, A complement is open. X belongs to A complement, and A complement is open set. X belongs to A complement and A complement is open set. So, we can use the definition of open set. Therefore, for x belongs to A complement, there exists some radius greater than 0 such that open sphere with that radius r and center x is totally lies inside this A complement, Here A is closed set, so A complement is open, or x belongs to A complement is open, so open sphere centered at x in A complement lies inside that A complement, SR of x lies inside A complement. This is the set of A complement. Now, this implies that this open sphere is totally lies inside A complement. Is this possible? Open sphere, if this open sphere lies totally inside A complement, then it is possible that this x is limit point of A. If this open sphere totally lies inside A complement, suppose this is metric space XD, this suppose set our A, then if the open sphere centered at x lies inside A complement, suppose this is A, then A complement set is this A complement. To get that open sphere inside A complement, our x must be somewhere here. If our x is at here, then the open sphere does not totally lies inside A complement, because it intersects A. If you take x is equals to this point, then again for any radius, that open sphere again intersects with A. So, we have to take x here, then for suppose this is radius and this open sphere lies inside A complement, this SR of x lies inside A complement, but if this x center x and radius r, this open sphere lies inside A complement, then it is contradiction to the fact that x is limit point. If x is limit point, then there for any radius greater than 0, that open sphere must intersect A. So, this is contradiction to x is limit point A. Here we have taken that x is limit point. Here we have taken that x is limit point of A. So, x is to be limit point of A, our x must be the either on the boundary or inside A, but this x is totally outside A, that is x is in A complement. So, this is contradiction to the fact that x is limit point of A. If our this open sphere lies totally inside A complement, this implies that this open sphere's intersection with A is totally empty. This open sphere lies inside A complement, this open sphere lies inside A complement implies that intersection of this open sphere with A is totally empty. So, this x is not a limit point, but this x was our limit point. So, this is contradiction. So, this shows that this SR of x lies totally inside A complement is show that this diagram is for your simplification. There is no need to write those diagrams in the proof. This shows that this SR of x does not contain any element of A. This shows that this SR of x does not contain any point or any element of E. So, SR of x does not contain any element of A. So, here we get some radius r such that open sphere's intersection with A is empty, but we have taken this x as limit point. So, this is contradiction, which is contradiction. To x is limit point of A. X is limit point of A. So, we have contrary suppose that x does not belongs to A, and we get some contradiction implies our x is the element of A, x belongs to A. Hence, we get set A contains all its limit points. We have proved that limit point of A is totally containing A. Hence, the proof of first part. Now, conversely, we will suppose this limit point A contains all its limit point, and we will prove A is closed set. Now, conversely, suppose A contains all its limit point, that is, this is sign of subset. Sorry. Now, our claim is A is closed set. A is closed set. To prove A is closed, we have to prove that its complement is open, that is x minus A or A complement is open. That is to show that, we have to show that this A complement is open. A complement means x belongs to matrix space X, but that X does not belongs to this set A. Now, to prove any set is open set, we just take any arbitrary element of that set and draw the open sphere, and that if that open sphere lies inside that set, then that set is open, and that open sphere does not lie inside that set, then we will say that that set is not open. So, by definition of open set, every element of this set, for every element of this set, there must some radius r such that the open sphere centered at that x must lies totally inside that set. Suppose here A complement. Now, let x belongs to A complement. X belongs to A complement means x belongs to x, but x does not belongs to A. x belongs to x, but x doesn't belongs to A. Now here this x is doesn't belongs to A, means x is not in the set A, and we have supposed that A limit point of A is subset of A. Now this x is not in A implies x is not in this set of limit points of A. X is not in this set A means x is again not in this set, because here we have taken A limit point of A is subset of A. Now for example, there is no need to write this example. If you take the set A limit point of A is equals to, suppose if you take set A is equals to 1 2 3 and suppose B is equals to 1 2 3 and 4, then if 5 is not in B, set B, any element which is not in B, and also you have taken that this A is proper subset of B, A is proper subset of. If any element is not the set of B, then how is this possible to that its element is in A? So if your element is not in the set A, then that again that element is not in A. So this is just a particular example. Now this x doesn't belongs to A, and also we have limit point of A is contained in A, that is A contains all its limit points. A limit point of A is subset of A. This implies x doesn't belongs to limit point of A. X doesn't belongs to limit point of A. Because of this, x doesn't belongs to limit point of A. So x doesn't belongs to set of limit points means we can find some radius R such that if we draw the open sphere with that radius at considering center x, then that open sphere's intersection with A is empty. Open sphere's intersection with A is empty means that open sphere lies totally inside A complement. So this is suppose metric space, and if we x doesn't belong, suppose this set A, and x doesn't belongs to limit point of A. The limit points of A are just the boundary points and interior points. This x doesn't belongs to doesn't belongs to A prime. A prime is the set of limit points. X doesn't belongs to set of limit points means x lies outside that limit points. X outside of that set A. Now if x is here, then we can find some radius greater than 0 and draw the open sphere which lies inside A complement, implies A complement is open. So x doesn't belongs to limit point of A means we can find, therefore we can find some radius greater than 0 such that SR of x is, there exists some radius greater than 0 such that SR of x lies inside A complement. This implies A complement is open. To prove A is closed, we have to prove A complement is open, and we prove any set open by taking the element of that set and to finding some radius such that the open sphere centered at that x is totally lies inside that set. Similarly, here SR of x lies totally inside that A complement. A complement is open, implies A is closed set. A is closed set. There is no need to draw these diagrams. This is for your simplification. So this is closed set. Hence the proof of this theorem. In this proof, first of all we have seen, first of all you have supposed A is closed and prove A contains all its limit point. In this converse part we have proved this A contains all its limit points, then A is closed set. This is the important result. Now we will take the example of limit point, another example of limit point. Suppose set A is given as the set of elements of the form 1 by n, such that n is the set of n is from set of natural numbers, and if you have to find the limit point of this set, then clearly this set is here. Suppose this real line, this is 0, this is 1. If you put the value of n is equals to 1, then you will get the set. This is not a proper answer. We just want to find the limit points, and we will write the limit points directly. Suppose this set is of the form, if we put the value of n is equals to 1, then we will get 1. Put the value of n is equals to, then we will get 1 by 2. If we put value n is equals to 3 and so on. This is the set, and we have to find the limit point of this set A. Limit points of this set A. To find the limit point of such sets, we just need the definition of limit points. The proper definition of limit point says that any element x is limit point, any element of x, that is any element of metric space is said to be limit point of set A whenever for all r greater than 0, for all r greater than 0 means for any radius, for each and every radius, if you draw the open sphere at that point, then that open sphere must intersect with A. Now, here if you take x is equals to 1 and take radius as suppose here our 1, then 1 by 2 is this element, then 1 by 3 is suppose this, then suppose 1 by 4 is here, 1 by 5, 1 by 6, 1 by 7 and so on. All these elements are the set of A. Now, if you take 1 and take this radius and draw the open sphere, then this open sphere contains one element of A, this one contains, this open sphere contains single element of this set A and that element is 1, but our definition of limit point says that open sphere must contains at least one point of A other than center, other than that x itself. So, here x is equals to 1 and this open sphere contains only that center, not any other point of A other than this x. So, this one is not limit point. Similarly, if you take 1 by 2 and draw this open sphere, then again this open sphere contains only center, that is only one element of set, this set A, and which is center. We have to find some elements in the intersection of A, that other than x, that open sphere must contain at least one point of A other than center. Here center is 1 by 2 and other than 1 by 2 there is no point of A in this interval. So, again 1 by 2 is not limit point. If you take 2, 3, 4, then there is no possibility of to be that element to be a limit point. Now, if we take 1 by 3, again we can find this. If you take 1 by 4, we can find this. Again if you take this element, so we can find some radius. After taking that radius, the open sphere does not intersect with A, that is that intersection does not contain any element of A other than center. So, these points are not the limit points, but if we consider 0, then for any smallest radius or the any largest element, there are some elements near to 0, because whenever our n tends to infinity, whenever this n tends to infinity, 1 upon n tends to 0. This implies that if we take, there are lot of many points near to 0 of this set A. There are lot of points of this set A near to 0. So, for the smallest radius, which is possible, for the smallest radius there are some elements of A other than 0. So, the limit point of A, that is limit point of this set is singleton 0, limit point of this set is singleton 0. So, 0 is the only limit point of A, because for 0 if we take any smallest radius or the largest radius and draw the open sphere, then that open sphere contains at least one point of A other than 0, because near to 0 there are lot of many points of this set, infinitely many points of set, this 1 upon n. Whenever our n tends to infinity, 1 upon n tends to 0 means these all the elements of the form 1 by n, for the larger values of n, these numbers are very close to 0, are in epsilon neighborhood of 0. So, that epsilon neighborhood, if you take that epsilon radius, smallest radius, then there are some elements of this set A. So, singleton 0 is the only limit point of this set 1 upon n, such that n belongs to set of natural numbers.